So we know there are many different elements in the universe, and we can nicely organize these elements through this periodic table of elements. However, what is the fundamental difference between different elements? For example, what is the difference between carbon and nitrogen and oxygen? Well, if we look at these different atoms, we see they have different protons. Carbon atoms have 6 protons. Nitrogen atoms have 7 protons, and oxygen atoms have 8 protons. And in fact, that's the way we define what an atom is. Whenever an atom has 7 protons, it is by definition nitrogen. Whenever an atom has 6 protons, it is by definition carbon. So if you have an atom in a lab and that atom has 54 protons, then you know by definition, without exception, it's a xenon element. So let's look a little closer at this nitrogen. So this particular nitrogen atom has 7 protons, 7 neutrons, and 7 electrons. But again, it has 7 protons, so therefore, by definition, this is a nitrogen atom. So something important to know is that a proton has a charge of +1. A neutron has a charge of 0, so therefore it's neutral. An electron has a charge of -1. So now that we know that, if we have this nitrogen and we throw on a neutron, what's going to happen? Well, we still have 7 protons, that hasn't changed. We've added a neutron, so now we have 8 neutrons, and we still have 7 electrons. So what do we have now? Well, we still have 7 protons, so by definition, this is still a nitrogen atom. The only difference is we've added a neutron. And what happens if we take away a neutron? Well, again, we still have 7 protons. We've lost a neutron, so now we have 6 neutrons, and we still have 7 electrons. But again, we still have 7 protons, so by definition, this is still a nitrogen atom. The only difference is we've lost a neutron. So again, all these atoms are still nitrogens. They all have 7 protons. The only difference is they have a different number of neutrons. So we call these isotopes. These are all different isotopes of nitrogen because they all have different amounts of neutrons. But what if we change the number of electrons? Well, if we add an electron, now we would have 8 electrons. But again, we still have 7 protons. So by definition, we still have a nitrogen. Remember, it's the number of protons that determines what kind of atom we have. But again, now we have 8 electrons. So therefore, now this nitrogen has a negative charge because we have 7 protons, so that's +7. And we have 8 electrons, so that's -8. So if you count up all those charges, you have a -1 charge. And the same thing if we take away an electron. Again, originally we have 7 electrons, now we have 6 electrons. So what do we have? Well, again, it's still nitrogen, 7 protons, so by definition it's nitrogen. However, if you were to add up all the charges, again, -6 plus a +7, so this has a net charge of +1. So this would be a positively charged nitrogen. But again, these are all nitrogen atoms. They all have 7 protons, so by definition, they're all nitrogen. The only difference is they have different amounts of electrons, so these are called ions. They're ions, and they have different charges because they have a different amount of net charge based on comparing the number of positively charged protons to the number of negatively charged electrons. So these are called ions. So the main point is that it's the number of protons that determine what the element is. And that's why we can see on the periodic table, we have the 6 next to this carbon. Because by definition, if an atom has 6 protons, it again is by definition a carbon. It's the number of protons that determine what kind of atom you have. So again, we have a carbon atom. We have 6 protons and 6 neutrons. But something important to know is that if we were to take 1 proton, it has a mass. It has a mass. If we were to look at 1 isolated proton, it has a mass of 1.6 times 10 to the -24 grams. And the same with a neutron. If we were to isolate 1 neutron, it would have a mass of 1.6 times 10 to the -24 grams. So therefore, if we were to find the mass of this carbon nucleus, we would just take the number of protons and add it to the number of neutrons. And if you were to do the math, you would see that this nucleus has a mass of 1.92 times 10 to the negative 23 grams. That's the mass of a single carbon nucleus. However, this is a really ugly number. 1.6 times 10 to the negative 24 grams is a very ugly, not whole number. So instead of dealing with this ugly number, we can use a Dalton. One Dalton is by definition 1.6 times 10 to the negative 24 grams. So this is an easier number to deal with. So if we were to isolate one proton, this one proton has a mass of 1 Dalton. And another way is instead of 1 Dalton, you can say it has a mass of 1 atomic mass unit. And the same thing with neutrons, because again, protons and neutrons have the same mass. So if we were to isolate one neutron, it has a mass of 1 Dalton, or you could say it has a mass of 1 atomic mass unit, which again equals 1.6 times 10 to the negative 24 grams. So again, these are just different ways you can define the mass of a proton or neutron. And again, a carbon atom has 6 protons and 6 neutrons, so therefore it has an atomic mass of 12 Daltons. Or you could say this carbon has an atomic mass of 12 atomic mass units. These are all just different ways to represent the atomic mass of carbon. And again, the atomic mass is the mass in the nucleus of an atom. So again, if we were to look at a nitrogen atom, again, 7 protons and 7 neutrons. So nitrogen atom has an atomic mass of 14 Daltons. And an oxygen atom with 8 protons and 8 neutrons has an atomic mass of 16 Daltons. So you can see this is a much easier unit of mass to deal with. But up here, I'm going to leave this key to show all these different conversions because these are really important and I'm going to refer to them throughout this video. But again, usually with chemists and biochemists, they like to use these Daltons instead of grams because again, we can use grams, but it's a really ugly number. It's much easier to use Daltons. But again, Daltons is the same as atomic mass units. If a nitrogen atom has an atomic mass of 14 Daltons, that means it has a mass of 14 atomic mass units. They mean the same thing. And again, if you were to use grams and count the number of these protons and neutrons in grams, you would get an atomic mass of 2.24 times 10 to the negative 23 grams. But again, this is an ugly number, so biochemists like to use Daltons. And again, the same thing with oxygen. If you do the math, you would get this mass for the atomic mass. And again, if we were to look at different isotopes of carbon, they would all have different atomic masses. And again, what about this particular atom? Well, we see it has 7 protons and 7 neutrons. So again, it has 6 protons and 7 neutrons. But again, it has 6 protons. So remember, whenever an atom has 6 protons, by definition, it's a carbon atom. But this happens to have 7 neutrons. So if you were to find the atomic mass of this carbon, it would be 13 Daltons. And the atomic mass of this carbon would be 14 Daltons. So these are all different isotopes of carbon. So what about the mass of water? Well, we have an oxygen atom, which has an atomic mass of 16 Daltons, and we have 2 hydrogen atoms, which each have an atomic mass of 1 Dalton. So therefore, this water molecule has a mass of 18 Daltons. And different amino acids have different masses because different amino acids have different R groups, but on average, the mass of an amino acid is 110 Daltons. And what about the mass of a glucose molecule? Well, if you were to add up all the protons and neutrons in this molecule, you would get a mass of 180 Daltons. So biochemists like to use Daltons when referring to the mass of different molecules. But remember, based on our key up here, 1 atomic mass unit is the same as 1 Dalton. So if a glucose molecule has a mass of 180 Daltons, it also has a mass of 180 atomic mass units. These mean the same thing. And the same thing with amino acids and this water molecule. So remember, there are 12 atomic mass units per 1 atom of carbon. So again, for carbon, there are 12 atomic mass units per 1 atom of carbon. So therefore, there are 12 grams per 1 mole of carbon. And this is just a relationship you have to memorize. And this is such an important relationship. I'm going to draw it up here. So that's true with any atom. For example, nitrogen, there are 14 atomic mass units per 1 atom of nitrogen. So therefore, there are 14 grams per 1 mole of nitrogen. And again, the same thing with any other atom or molecule. For example, glucose has 180 atomic mass units per 1 molecule of glucose. So therefore, there's 180 grams per 1 mole of glucose. So these are just important relationships you need to just memorize. And again, remember, atomic mass units are the same as Daltons. So therefore, if 1 atom of carbon has a mass of 12 Daltons, then that also tells you that there are 12 grams per 1 mole of carbon. So these are just relationships you need to memorize. But if you want to understand why this relationship is true, first you need to understand what a mole is. What is a mole? Well, to illustrate this, what is a dozen? Well, we know if we have 12 bread rolls, we have a dozen bread rolls. If you have 12 apples, you have a dozen apples. If you have 12 cars, you have a dozen cars. So again, a dozen is simply a number. It's 12. If you have 12 of anything, you have a dozen of whatever that is. So the same thing with a mole. A mole is just a number. When you have this number of cars, then you have 1 mole of cars. It's just a number. Just like if you have 12 cars, you have 1 dozen cars. If you have this many cars, you have 1 moles of cars. It's just a number. And again, chemists don't like using those big numbers, so we like to use scientific notation. So if you have 6.022 times 10 to the 23 cars, then you have 1 mole of cars. So this number is referred to as Avogadros number. And this is such a large number. You might think, why do we care about this arbitrarily large number? Well, when we're dealing with atoms and when we're dealing with trillions and trillions and trillions of atoms, it's convenient to deal with these large numbers. So we've created this unit of number, which is we call Avogadros number. So 1 mole of anything is just when you have this many of whatever it is. You have Avogadros number. And this is such an important relationship. I'm going to draw it up here. So this is something else you just need to memorize. So again, I like to think of it kind of like a dozen. You have a dozen of whatever, but again, instead of 12, it's this number. So again, if you have 6.022 times 10 to the 23 atoms of carbon, you have 1 mole of carbons. And again, if you have that many number of glucose, you have a mole of glucose, and etc. And again, if you have this many carbons, you have 1 mole of carbon. So if you have double this amount, so if you have double that amount, you have 2 moles of carbon. Just like if you had 24 cars, you would have 2 dozen cars. It's the exact same idea. So again, remember this important relationship. For carbon, there are 12 atomic mass units per 1 atom of carbon. So therefore, there are 12 grams per 1 mole of carbon. And again, we said this is an important relationship you just have to memorize. But if you really want to understand why this is true, first, we can take these atoms and convert it to moles using this conversion factor. Again, we know this conversion factor. There are 6.022 times 10 to the 23 atoms per 1 mole. So using this conversion factor, we can take atoms and convert it to moles. And we can also use this conversion factor. Again, we know 1 atomic mass units has a mass of 1.6 times 10 to the negative 24 grams. These are just 2 different units of mass. So we can use this conversion factor to convert this atomic mass units into grams. So using these 2 conversion factors, what do we get? Well, again, atoms will cancel and atomic mass units will cancel. So what are we left with? Grams and moles. So now we have grams per moles. And if you were to do the math, you would get 12 grams per 1 mole of carbons. So that's the math to prove that this is true. But again, the point is, there are 12 atomic mass units per 1 atom of carbon, so therefore there are 12 grams per 1 mole of carbon. And again, the same thing with nitrogen. There's 14 atomic mass units per 1 atom of nitrogen, so therefore there are 14 grams per 1 mole of nitrogen, and etc. So this is just a relationship you should memorize. So again, going back to the periodic table, if we were to focus on this nitrogen, we see there's a 7 up here. Why? Because remember, by definition, the convention that chemists have decided to use is whenever an atom has 7 protons, by definition, it's nitrogen. So that's why we have this on the periodic table. And this bottom number essentially represents the atomic mass, which also, remember, can represent the number of grams per mole, or it can represent the atomic mass units per 1 atom of nitrogen, or the number of Daltons per 1 atom of nitrogen. So that's what these numbers mean on the periodic table. So if you're taking a chemistry class, or if you're taking the MCAT, there's a common question that's asked in chemistry classes, and you'll see in college, where you have the number of grams of something, so then you need to find the number of moles, or the number of atoms. For example, let's say you have a chunk of carbon. Let's say you have 46 grams of carbon, and you're asked to find out how many moles of carbon you have. If you have this 46 grams of carbon, how many moles of carbon atoms do you have? Because again, if we have 46 grams of carbon, we know we have lots of atoms of carbon. So how many moles of carbon atoms? Well, again, we just need to use this conversion factor. We know, based on all these things we've learned, we know this bottom number essentially tells us the number of atomic mass units per 1 atom, which also tells you the number of grams per mole. So this conversion factor can take us from grams to moles for carbon. So using this conversion factor, we know there are 12 grams of carbon per 1 mole of carbon. So again, the grams will cancel and we're left with moles. So now we have moles. And again, if you do the math, you would get 3.83 moles. So now we know if you have 46 grams of carbon, you have 3.83 moles of carbon. So now that we know how many moles of carbon we have, how many actual atoms of carbon do we have? Well, again, we know the conversion factor from moles to atoms. We know there's 1 mole for 6.022 times 10 to 23 atoms. That's the conversion factor, which again, we already explained earlier. So using that conversion factor, we know we just multiply by this conversion factor. So the moles cancel and we're left with atoms. So now we get our answer in units of atoms. And again, if we do the math, we get 2.28 times 10 to the 24 atoms. So now we know if you have 46 grams of carbon, you have this many atoms of carbon. So again, this is a common operation you'll do in a chemistry class, going from grams to moles and then moles to atoms. So this process you should just memorize. So how about another example? Let's say we know how many molecules of glucose we have. Let's say we have 7.78 times 10 to the 22 molecules of glucose. How many grams of glucose? If we have this many molecules of glucose, how many grams of glucose? Well, again, we know how to go from molecules to moles to grams. So again, we know looking at a glucose molecule, there's 180 Daltons of mass per glucose molecule, which means there's 180 atomic mass units per molecule of glucose, which means there's 180 grams of glucose per 1 mole of glucose. So again, that's our conversion factor from grams to moles. So again, we know the conversion factor from molecules to moles. We know that's just Avogadros number. So that's constant. So that's how you go from molecules to moles. And we know how to go from moles of glucose to grams of glucose using this, essentially this atomic mass. So now we know the two conversion factors needed to go from molecules to moles and then moles to grams. So now we just do the math. So again, we were given 7.78 times 10 to the 22 molecules of glucose. So knowing that, we know how to go from molecules to moles. We just use Avogadro's conversion. And we know how to go from moles to grams. That's just essentially the atomic mass. And again, we explained how to do that earlier. So now we see the molecules cancel and we see the moles cancel. So we're left with units of grams. So our answer will be in units of grams. And if you now just do the math, you get 23.2 grams. So now we know if you have 7.78 times 10 to the 22 molecules of glucose, you'll essentially have 23.2 grams of glucose. So this is a common operation you'll see in chemistry. In chemistry, you constantly need to go from molecules to moles, moles to grams, or grams to moles, moles to molecules. That's something very common in chemistry. So one last example. Let's say you have this balanced chemical reaction and you have the stoichiometry and the balanced chemical reaction. So let's say you have 47 grams of methane. And let's say it reacts with an unlimited amount of oxygen. You might wonder, how many grams of water will we produce? So if you just sit down and think conceptually, this will be a very complex question. However, there are simple operations you can do to figure this out. So again, we're given 47 grams of methane. So you go from grams of methane to moles of methane. Then you go from moles of methane to moles of water. So again, moles of methane to moles of water. Then you go moles of water to grams of water. Because again, that's the question. How many grams of water is produced? So again, if we were to look at one molecule of methane, we would see it has a mass of 16 atomic mass units. And again, looking at one molecule of water, it has a mass of 18 atomic mass units. And again, we know this important relationship. If you know the number of atomic mass units per molecule, you know the number of grams per 1 mole. And again, the same thing with water. So now we know how to go from grams of methane to moles of methane. This is the conversion factor. And we know how to go from moles of water to grams of water. This is the conversion factor. However, how do you go from moles of methane to moles of water? So again, if you were to sit down and think about this very abstractly, it would be a very complicating question. But it's actually really easy. All you need to do is look at the balanced equation. You just need to look at the stoichiometry of the balanced equation. And we see, based on the stoichiometry, 1 molecule of methane is needed to produce 2 molecules of water. So that's our conversion. 1 mole of methane is needed to produce 2 moles of water. And again, in chemistry, we like to deal with moles rather than molecules. Because again, we're dealing with so many molecules, it helps to work with moles instead. But again, that's the conversion of going from moles of methane to moles of water. You just look at the balanced equation. 1 molecule of methane is needed to produce 2 molecules of water. So again, instead of dealing with molecules, you use moles. But the math works out the same. So now we know the conversions. We know how to go from grams of methane to moles of methane. We know how to go from moles of methane to moles of water. And we know how to go from moles of water to grams of water. We have all the conversion factors. So again, we were given 47 grams of methane. And again, we know how to go from grams of methane to moles of methane. We know then how to go from moles of methane to moles of water. And then we know how to go from moles of water to grams of water. And again, if we were to cancel out all the units, grams of methane cancel, moles of methane cancel, moles of water cancel, and we're left with grams of water. That's the units we're left with. So our answer will be in grams of water. And again, if you just do the math, if you just do this math, where again, 47 times 1 divided by 16 times 2 divided by 1 times 18 divided by 1, you would get 105.75 grams of water. So again, if you have 47 grams of methane and it were to react with an unlimited amount of oxygen, you would produce 105.75 grams of water. So again, this is another very common operation you'll see in chemistry. And in the link below, I'll go over lots of different examples. And I really think just seeing a bunch of examples over and over again in a very repetitive manner will really help illustrate and really help memorize what's going on.